Have you ever looked at a map of the world and just, fallen for the illusion? We see all these massive blue spaces and assume it's just one giant uniform global ocean, right? I mean, we're the ones who drew imaginary lines and slapped different names on different parts. But what if I told you that nature actually drew some of its own lines? We're talking real, living, and honestly, stunningly clear borders right out there in the open water. Welcome to this explainer. Today, we're diving into one of the absolute most astonishing geographical marvels on Earth. We're going to look at a massive, literally invisible wall where the world's two largest oceans meet but utterly, stubbornly refuse to mix. So let's set the scene here. Picture yourself traveling all the way down to the southern tip of South America, to a beautifully rugged spot called Cape Horn. This is where the vast Atlantic Ocean and the mighty Pacific Ocean crash right into one another. But instead of blending together into a giant murky soup, something really bizarre happens. They just stop. It begs the question, is there an actual invisible wall in the ocean? I mean, what kind of mysterious force could possibly prevent two of the absolute largest bodies of water on Earth from simply mingling? It's a visual anomaly that just completely defies our everyday intuition. The contrast you see at this border is just mind-blowing. Along the 800-kilometer stretch known as the Drake Passage, there's a stark visual divide. On one side, you've got the noticeably lighter, clearer water of the Atlantic, and right up against it, the darker, deeper-looking water of the Pacific. It's so awe-inspiring that the legendary explorer Jacques Cousteau was totally mesmerized by a very similar thing during a deep dive in the Strait of Gibraltar. The boundary is so sharply defined that it honestly looks like CGI from a sci-fi movie, but it is 100% real.
Moving into part one, we're looking at the invisible wall between oceans.
And that brings us to section 2, the scientific secret of ocean clines. Now, to solve this puzzle, we definitely aren't relying on magic. Like any good detective story, we already have all the clues we need to piece this together. We just need to look past those dramatic surface colors and introduce our primary suspect, which is an ocean cline. So what is that? Well, an ocean cline is basically an invisible border between two water bodies, caused entirely by differences in their physical and chemical properties. When two bodies of water have distinctly different makeups, those differences act like a massive invisible shield, making it incredibly hard for them to blend. So it turns out the crazy color difference on the surface is really just a visual symptom of a massive chemical divide happening way underneath. Let's break this down a bit further, because, well, not all clines are created equal. There are 3 primary types we need to investigate here. First up is a thermocline, which is a border created by differences in water temperature. Second, we have a halocline, and that one is driven by differences in salinity, or saltiness. And finally, the third is a chemocline, formed by different chemical and biological compositions. To figure out exactly what's happening down at Cape Horn, we need to put these 3 possibilities to the test. Let's start by looking at the thermocline. And you know what? You can actually recreate this in your kitchen right now. If you fill a basin with both hot and cold water and just carefully watch it, you'll see a clear separation. The hot water expands, which drops its density. Because of that, the lighter, warm water naturally rises to the top, while the heavier, cold water sinks right to the bottom. Out in the wild, this exact thing happens when the warm water of the Gulf Stream hits the freezing cold water of the North Atlantic. It's super cool, but is temperature the main culprit for our Pacific Atlantic wall? Well, not quite. So, we move to our next suspect, chemoclines. This is where unique chemistry and plant life create an isolated pocket of water. A really famous example of this is the Sargasso Sea. It's this absolutely incredible body of water that has literally no land borders at all. It is entirely contained within the Atlantic Ocean. Because of its highly unique sea meads and its specific chemical makeup, it just doesn't mix with the rest of the Atlantic. Fascinating stuff for sure. But again, it's actually not the primary force separating our 2 massive oceans at Cape Horn. Which brings us to section 3. The impact of salt and density. That leaves us with the third, and frankly, the most spectacular suspect, the halocline. The true architect behind our invisible wall is all about salt, and the magic number here is 5. The Atlantic Ocean is at least 5 times saltier than the Pacific Ocean. That is a massive difference in salinity, and it fundamentally alters the density of the water. We aren't just talking about a minor variation here. It's a profound structural difference that creates an incredibly powerful halocline right where they meet. We can prove exactly how this extra salt changes the water's density with another really simple everyday experiment. If you grab 2 glasses of water, leave one totally plain, but stir several tablespoons of salt into the other, you've just fundamentally changed the physics of that water. Now drop an egg into both. In the freshwater, the egg is going to sink straight to the bottom. But in the salt water, it floats. The salt makes the water so dense and so heavy that it can literally support the weight of the egg. The Atlantic Ocean is essentially that heavy, super salty glass of water, while the Pacific is much, much lighter. But hang on a second. If you've been following the logic so far, you might have just spotted a pretty massive paradox. If the salty Atlantic water is heavier and denser, basic physics tells us it shouldn't just stand side by side with the lighter Pacific water like some vertical wall. The heavier water should immediately sink and flow directly underneath the lighter water. Yet, as we see at Cape Horn, they stand vertically, right next to each other. So why on earth doesn't the heavy water just sink? Let's look at Section 4, the amazing work of the Coriolis force. This paradox brings us to the real plot twist in our explainer. To solve this sinking water mystery, we actually have to zoom out from the ocean itself and look at the entire planet's rotation, specifically a little something called the Coriolis force. The Coriolis force is basically an inertial force that deviates the path of moving objects because the Earth is rotating. In really simple terms, our planet is constantly spinning. And because it's spinning, anything moving across its surface, especially giant oceans, doesn't just travel in a straight, boring line. The Earth's rotation physically pulls and curves the path of that moving water. Because of this Coriolis force, ocean currents in the northern hemisphere are deviated clockwise. But in the southern hemisphere, which is exactly where Cape Horn is located, they deviate counterclockwise. This acts like a giant, invisible hand guiding the oceans. The currents of the Atlantic and the Pacific are forced into paths where they only touch for a brief, fleeting moment before the Earth's spin literally forces them to turn away from one another. They simply don't have the time or the momentum to push over and mix. And there's actually one final layer to this puzzle that stops them from mixing during that super brief encounter. It's called molecular cohesion. See, water molecules are highly cohesive. They really strongly like to stick to their own kind. It takes a ton of energy to force two totally different bodies of water to blend. We see this all the time, not just in the deep ocean, but even where rivers meet the sea, like up in Canada with the Fraser River emptying into the Strait of Georgia. That strong cohesion holds the different waters together in their own separate masses. So yeah, maybe a tiny bit of mixing happens over incredibly long periods, but the contrasting flows and those tight molecular bonds keep the oceans visually and physically distinct. Moving on to our final section, Part 5, Other Examples Around the World. Now, you might be sitting there thinking, this is just some freak, one-off geographical fluke at the bottom of the world. But nature is highly consistent. The rules of temperature, speed, and density apply everywhere, even in everyday freshwater rivers. Down in Brazil, near Manaus, the Rio Negro and the Sulamos rivers crash into each other, but absolutely refuse to mix for up to 6 miles. They create a massive thermocline just because of their different temperatures and speeds. We see it in Germany too, with the Moselle and the Rhine. And in the German city of Passau, there's this stunning three-way intersection where the Ilz, the mighty Danube, and the Inn rivers all meet, and they maintain distinct lanes of water because of these exact same physical barriers. It's wild. Take those German rivers we just mentioned, for example. The Rhine River flows light and incredibly clear, while the Moselle River runs right alongside it, but it's totally dark and murky. It completely reinforces everything we've talked about today. Whether it's the giant 800-kilometer Drake Passage between oceans, or just a river junction in Europe, when water bodies have distinct physical and chemical personalities, they're going to throw up an invisible wall rather than lose their identity. So, there you have it. We've solved the mystery. It isn't some ancient magic separating the Atlantic and the Pacific. It's a gorgeous, highly complex dance of salinity, the Earth's rotation, and just sheer molecular stubbornness. But I want to turn this over to you for a second. Do you know of any other seas or rivers around the world that refuse to mix? Have you ever actually seen these invisible physical forces at play during your own travels? Think about it, and definitely keep an eye out next time you're looking out over a body of water, because there is always a totally invisible world of physics happening right beneath the surface. Thanks so much for joining me on this explainer, and keep learning.